Yeah.
I've done it once. To go. Hypnotized by the numbers.
I was chatting away there. Mhm. Hello, everyone, and welcome to the March Recreational Astronomy Night meeting of the RASC Toronto Centre. My name is Paul Markov, and I'll be your host for this evening, as usual. We are at the Ontario Science Centre in front of about, 22, 23 people. For our online viewers, if you can, please join us next time here at the Science Centre. For those who cannot come in person, rest assured that the online presentations will continue. And as always, I'd like to thank our top-notch AV team, comprised of Andrew and Better Reed, Ward LeGros, and a few others who I don't see here tonight. But there's always lots of help to get these broadcasts online. As you know, I'm always searching for presentations, and we have one open slot for the April 3rd meeting, and that meeting is just before the solar eclipse, FYI, so we're not going to be having any solar eclipse presentations at the April 3rd meeting. So if you have a presentation in mind, or if you know somebody who may be willing to present, please get in touch with me. And the solar eclipse presentations will happen on at the May 1st meeting. And I imagine, I'm hoping we're going to have a lot of people wanting to present and show us their photos and talk about their experience. So it's going to be first come, first served in terms of being able to present. So after you observe it, photograph it, please get in touch, and we'll set you up with a presentation slot. I am hoping that there's going to be a lot of people who want to present, and that those presentations will have to spill over into the June meeting. All right, the speakers for this evening are Arnold Brody, presenting the sky this month. We have Arushi Nath, and she'll talk about integrating sparse and dense photometry methods for improved asteroid property analysis. And then we'll have Michael Watson, who is our national president and experienced solar eclipse chaser, and he'll talk to us about how to photograph solar eclipses. Our Toronto Centre President, Tom Luton, will close the meeting with announcements as usual, and we expect to be done around 9:30. If you're watching us online and have a question, please enter it in the YouTube chat box, and someone here, probably Ward, will ask the question to the speaker on your behalf. In the room, if you have a question, put your hand up, wait for me to hand over a microphone, and then ask your questions so that people online can hear the question. And a show of hands, do we have anybody here for the first time, whether you're a member or not? It doesn't matter. Good, I see a few people. Welcome. And let's see, I think we're ready to get going. Before we start with Arnold, I'd like to invite Tom to do an award presentation.
Thank you, Paul. Evening, everybody. One of the joys of being president is handing out awards. So the province of Ontario has a volunteer service award. And this year, one of our recipients of the Youth Award is in here tonight because she's giving one of the presentations. If you were here with us last month, I gave the full description. We had several award winners. But tonight, we would like to acknowledge and congratulate Arushi Nath for her award. Okay, Arnold, you're up.
Okay, so our next speaker is Arnold with The Sky This Month.
Well, thank you, Paul, and hello, everyone that's here and watching online. I'll talk about what's up in the sky for the rest of March and the start of April. Unless I mention otherwise, I'll be referring to the sky as seen from Toronto. This is a month of transitions. We transition from winter to spring, from standard time to daylight savings. As the Orion spur, filled and surrounded with open and globular clusters, sinks further to the west, we gaze out into intergalactic space and we transition to the galaxy hunting season. The highlights for March include a Moon-Venus pairing tomorrow morning, Algol at minimum this Saturday night for those in the Eastern and Central time zones. Daylight savings begins on Sunday morning. New moon is on the 10th in Universal Time, late on the 9th in the Americas. This coming weekend is a perfect Messier Marathon opportunity. More about that coming up. The moon is close to Jupiter on the 13th and very close to the Pleiades the next night. For those in the Southern Hemisphere, the Gamma Normid meteor shower peaks on the 14th. The sun crosses the equator heading north on the 20th. And there's an excellent chance to see Mercury late in March, and the full moon on the 25th passes through Earth's penumbral shadow. In addition to those highlights, there are some benefits observing in March. For this March, we have a new moon weekend before daylight saving kicks off. There's a chance to observe all object types, planets, globular and open star clusters, galaxies, asteroids, 2 comets, and a meteor shower visible from the Southern Hemisphere. One last chance to see the winter constellations while seeing the spring and summer constellations rise throughout the night. And for those of us in the northern climes, we start to enjoy some warmer conditions. And there are no mosquitoes yet, right? I include astronomical twilight with night in what I call the observing window, since the planets and brighter deep space targets can be observed during astronomical twilight. This window is narrowing at the quickest rate of the year this month, as you can see from this hourglass shape of the night window. The observing window is 10.5 hours long tonight, shrinking to just 9 hours by the start of April. That's a big drop of 1 hour and 23 minutes. Night shrinks even more. Come September, those minuses turn to pluses. Dark skies with little or no moon appearance is with us now, with new moon this weekend, and the darkness continues a bit into next week. The full moon on the 25th goes by a number of names. It goes by the worm moon, or the crow moon, or the crust moon, the sap moon, or the sugar moon. How about the Lenten moon, the pure moon, and most recently the pothole moon? And dark skies will return the first week of April. Now let's begin our tour of the night sky with a look at the inner solar system. Currently, Mercury appears too close to the sun to be observed, but it will climb higher in the west over the next few weeks. Venus's elongation is 22 degrees west of the sun, making it possible to catch it just before sunrise. Venus is racing around the sun faster than us, so it will fall further behind it and lower in our morning sky this month. Mars is a bit higher at 30 degrees west, though still low at sunrise because the ecliptic hugs the horizon on spring mornings. Its separation from the sun will grow a bit this month. Mercury reaches greatest elongation east of the sun on March 24 and becomes an easy catch. At the start of April, Venus has fallen too close to the sun for observing, while Mars has climbed a bit higher in the pre-dawn sky. Mercury reaches its greatest elongation east of the sun, 18.7 degrees on March 24. With the ecliptic standing tall on spring evenings, the little planet will sit 13 degrees high at 8 p.m. when the sun has dropped 5 degrees below the horizon. Mercury should be bright enough to see in the twilight at magnitude 0.75 through 4.4 air masses. The ecliptic stands even taller the following evening, lifting Mercury another 13 arc minutes with it, even though its elongation has begun to fall. Now, I'm not sure if you can push an 11-inch telescope to 900x, but if possible, Mercury would appear slightly crescent. Tomorrow morning, you can use an old crescent moon to help you find Venus 18 degrees to its left just before sunrise. If it's possible to magnify Venus enough, it would appear gibbous as it starts to move around behind the sun. You can also use the moon tomorrow morning to help you find Mars, 11.5 degrees or just wider than a fist at arm's length to the left of the moon. Mars is higher in the morning sky at the start of April, though it still appears as just a reddish dot, just 4.5 arc seconds wide. When we eventually reach opposition with the little Mars next winter, it will be a meager, call it 15 arc seconds wide, needing a very large telescope to see any details. Now, summertime oppositions of Mars are the best, and we finally get one 10 years later in September 2035, when Mars will grow to 24.62 arc seconds wide. I think 25 arc seconds is about as best as it ever gets. So that's going to be good in September of 2035. By the way, that's Saturn photobombing the scene, reminding us to check out the outer solar system, so let's do that now. Tonight, Uranus and Jupiter will appear fairly close to each other in the evening sky, while Neptune is lost behind the sun and Saturn is also too close to the sun to be seen. By the start of April, Uranus and Jupiter have drawn even closer together. Neptune is still lost in the sun, while Saturn has edged slightly further from the sun in the dawn sky. Jupiter was at its best for observing this past fall and winter and remains a bright beacon in the west and easy to spot. Jupiter is getting lower each night and will slide behind the sun in May. Now, once you spot Jupiter, you can then find Uranus less than a fist to its upper left at magnitude 6.16 due to our atmosphere. Uranus might now be too dim to spot by eye alone, but Uranus is close to 3, that's interesting. Notice there, Uranus is close to 3 light hours away from us, giving you some sense of the scale of our solar system. The light we see from Uranus is even 3 hours older when you add the time the sun's light took to get there and bounce off. You might still see some details on Jupiter, although the globe is getting pretty small as we move towards our greatest separation from Jupiter in May. The gap between Jupiter and Uranus shrinks to just 3 degrees by the start of April. Saturn is hidden by the sun's glare at this time, barely above the horizon at sunrise. There is a challenge that you can attempt on Friday, March 24, around 7 a.m., when Venus and Saturn appear a little over a half a degree apart. It's challenging because the sun will be rising in just a few minutes. You won't have much time. You will need an unobstructed view to the east. Higher elevation, like a high-rise apartment, would help. And Saturn's magnitude is reduced by thick atmosphere. So you may need a bit of luck, but you should be able to do it, especially with the help of binoculars. By the beginning of April, Saturn will be slightly higher before sunrise, but still just a dot. We'll have to wait a few more months before Saturn grows large enough to observe. But you won't have to wait for Comet 12P Pons-Brooks, which is currently in Andromeda, 1.7 AU from Earth. Yesterday, an observer with 50 millimeter binoculars posted an estimated magnitude of 5.9 for the comet, with a coma 8 arc minutes wide. He posted that on the Comet Observers database. It will remain visible in the west for mid-northern latitudes throughout the month. Here's the path the comet will trace in March. The comet stays comfortably above the western horizon, giving us well over an hour to observe it in a darkening sky. Now, on March 22nd, there's an opportunity to view and image the comet as it glides by M33, the Triangulum Galaxy, which is 3 degrees northwest of the comet. By the start of April, the comet will be crossing Aries and brightening, possibly to naked eye visibility. It is already an easy binocular target. And here's an image taken by, is that a robotic telescope? I forget. Yeah, it's the Virtual Telescope Project took that picture about 3 weeks ago, so you can see it's starting to sprout a nice tail. Pons-Brook might be bright enough to be seen during the upcoming solar eclipse. What an amazing sight this will be, with the comet's tail pointing at the Pleiades, and Jupiter and Venus on opposite sides of the eclipsed sun. Truly spectacular. Oh, it's got to be clear that afternoon. It's gotta. Now, for early risers, there's a second comet you can easily find with binoculars. C2021S3 at an estimated 7th magnitude. It's just a little too dim to see without binoculars or a telescope. Imagine if it were brighter. We'd have 2 naked eye comets at the same time. That would be awesome. But still, this is very bright, binocular easy. And here we see its path across the eastern sky through March. Each dot is a night. Notice how evenly spaced the dots are, suggesting the comet is not moving drastically towards or away from us, but simply passing us. The comet was discovered by one of the Pan-STARRS robotic telescopes more than 2 years ago. Here we see the comet's path in that diagram. It's already passed the sun about 3 weeks ago, and it is now passing us, closest on March 14. So there's the comet, there's us, and it's just passing us right by this month. Now, unlike Pons-Brooks with a frequency of 71 years, this comet, C2021S3, is an Oort cloud comet with an orbital period over 1 million years, close to 2 million. On March 28th through the 31st, we have a great opportunity to observe and image the Oort cloud visitor passing by the Coat Hanger cluster. That'll be nice. On to the sun now. There are no active sunspots regions currently aimed at Earth, which would explain the low auroral activity recently. The NOAA Space Weather Prediction Center does not anticipate any solar storms from now to March 10. Two new active regions are rotating into view, 3599 and 3600. 3599 has 12 spots, has doubled in size in the last 3 days, is bipolar, and the positive and negative spots are not well separated, which means they could set off some fireworks. Meanwhile, 3600's lone spot doesn't have a dance partner to make sparks with. These regions have now rotated about halfway towards us. The lack of Earth-facing eruptions doesn't mean the sun is quiet. This 48-hour time lapse of the sun in 304 angstroms show magnificent loops, flares, and prominences across the sun's surface and limb. You'll notice that this activity is getting closer to the sun's equator, and that's a sign of a solar cycle reaching its maximum. I don't know if you noticed that there, but did you see that plasma mountain over here? I'll just drag this back a little bit here and let it run. It's over here in this area. It is so tall. You see it? Amazing. And then there's a big eruption down here, flares all over the place. Okay. In spite of the lack of auroras the last week or so, we are in an eclipse season, which occurs around both equinoxes. Historical records show geomagnetic storms fueled by the sun, which trigger the auroras, are twice as likely at the equinoxes than in summer or winter. Now, the reason for this is explained by the Russell-McFerrin effect, named after the UCLA researchers who first explained it. Basically, the cracks are opened by the solar wind itself. South-pointing magnetic fields inside the solar wind oppose Earth's north-pointing magnetic field. The two, north versus south, partially cancel out one another, weakening our planet's magnetic defenses, and this cancellation can happen at any time of the year, but it happens with the greatest effect around the equinoxes. There are weak spots at the magnetic poles where the magnetic field lines don't provide much protection, allowing charged particles to penetrate easily. And that explains why there are constant auroras around those ovals that are around the North and South Pole all the time. When the magnetic poles don't point at or away from the sun, as during the equinoxes, these weak spots align with the sun's magnetic field lines, allowing the charged particles to flow in. So as soon as we get another good outburst from the sun, we will get auroras. Now, new moon. That occurs on Sunday, March 10, when the moon's at perigee, which bodes well for the next new moon in April. Beheim crater tips our way on the 13th. First quarter occurs on the 17th. Oken crater is tipped our way the next night. The moon is at apogee on the 23rd, and then full on the 25th. Lavoisier crater is tipped our way on the 31st, and last quarter occurs on April the 2nd. Last month, Intuitive Machines' Odysseus moonlander soft landed at 80 degrees south latitude at Malapert A, a smooth elevated plateau free of deep craters and large boulders as seen here in this LRO close-up. Unfortunately, someone forgot to turn on Odie's laser rangefinder back on before liftoff, and a NASA experimental navigation system that was hitching a ride was patched in to take over with just 2 hours left before landing. Although Odie survived the landing, it was moving laterally too fast and tore off one of its legs and tipped over, although not necessarily the full 90 degrees suggested by CEO Altimus. Maybe a little less than that. They think it may be resting against another boulder about 30 degrees tilted. But some of its antennas are aimed down and some of its instruments are aimed down, so they can't be used, but there is at least some communications available. And some of its solar arrays were able to see sunlight a bit before night fell 2 days ago. So its batteries will definitely won't have enough power to keep it warm until the next sunrise, keep it warm throughout the lunar night. But there is a chance that Odie will revive at sunrise later this month, just like the Japanese Slim lander did last month. Slim also tipped over when it was landing. The abundance of water ice on the moon's permanently shadowed craters at the moon's south pole has drawn efforts worldwide to explore the region. On Tuesday, March 19, this region is perfectly illuminated for you to explore near Malapert A. The Explore the Moon observing program includes 2 craters, Clavius and Imaginus, the southernmost craters in the ETM program. They are both large craters. In fact, Clavius is the second largest crater on the Earth-facing side. Clavius is lacking a rim if you look carefully. It's like a pothole. It features a semicircle of ever-decreasing craters stretching across the floor. I believe the biggest one on the rim, I think that's Rutherford. Meanwhile, Imaginus is a much older crater, and it's nearly devoid of features, other than clusters of craters on its eastern rim. Regarding the highlights listed at the start, here's another look at the Moon-Venus pairing tomorrow morning for those with clear skies, and I think it will be clear tomorrow morning here in the Toronto area. You might find Mars between them with binoculars. There's a lovely conjunction of still bright Jupiter and a young crescent moon on Wednesday, March 13. The pair will make a great sight in stabilized binoculars. The following night, the Pleiades, the crescent moon, Uranus, and Jupiter make a vertical lineup after dark. As Thursday night turns to Friday morning, the moon draws ever closer to the Pleiades, coming within a degree before they set around 1:15, tight enough to frame in a low power view. Stargazers south of latitude 26 degrees north may catch meteors from the Gamma Normid shower that peaks on the night of March 14-15. Zenith hourly rates have varied over the last few years, mostly in the single digits to low teens. The meteors hit the atmosphere at 68 kilometers a second. That is fast, so they can be bright, and some will produce trains. The full moon on March 25 will pass through Earth's penumbral shadow, slightly dimming its appearance. You might not notice the difference, even at mid-eclipse at 3 in the morning. So I'm not so sure this is really a highlight, perhaps, especially at 3 in the morning. On to deep space. For those in the Eastern or Central time zones, if you have clear skies this Saturday night, there's an excellent opportunity to watch the eclipsing binary star Algol drop 75% in brightness from the onset of darkness to 10 p.m. Eastern time or 9 p.m. Central time. That's how long it will take to fully darken or dim down. Algol is the second brightest star in Perseus. Look to the upper left of Cassiopeia for bright stars in a pair of curves. The brightest is Murphak at magnitude 2, and next is Algol, just slightly dimmer at 2.1. However, every 2.87 days, dimmer Algol B blocks most of brighter Algol A, and the total magnitude we see drops to 3.4. Still visible, but significantly dimmer, enough so to have stoked fear in ancient times, earning it the name the demon star and the head of Medusa. If you are out Saturday night observing Comet Pons, Brooks, and other nearby targets, take a moment every 15 minutes or so to compare Algol to the other stars in this chart to monitor its drop in magnitude. Search minima of Algol to find sites offering timings of upcoming minima and star charts like this one with the magnitudes of neighboring stars for making comparisons. A Messier Marathon is an all-night attempt to find all 110 objects in the Messier catalog. 16th and 17th century Charles Messier found 41 of the 110 faint fuzzies while hunting for comets. He also included objects found by contemporaries. A few were added posthumously. Now, marathons are possible in March when the sun sits in a patch of sky where there are no Messiers. The hunt begins as soon as the sky darkens to astronomical twilight and will run all night. I believe there's a break possible around 1 a.m. For Toronto Centre members, Chris Vaughan has provided an update for the marathon plan for this weekend at the Carr Astronomical Observatory. 10 members have registered, leaving 7 beds still available. Unfortunately, the Friday through Saturday night period looks cloudy. Though that could change, Chris says he'll open the CAO if the forecast clears. He also warns us that a small section of the road to the CAO is extremely rutted and would be treacherous going for inexperienced drivers and small cars, especially at night. Now then, to complete as much of a marathon as possible, you'll need a list of the objects in observing sequence. And one good source is provided by AstroTom. His homepage offers a link to a spreadsheet that you can download and print for taking to the field. You record the time when you spot each object for tracking your progress. Many marathon lists start with galaxies M77 and M74, though some put M45, the Pleiades, at the top since they will be visible before those two galaxies are. You will probably prefer to use lower magnification than you would for detailed observing in order to improve your chances of finding the target quickly and saving time. Now, here we see our first target, M77, with 60 times magnification. You won't want to linger here for long because you'll want to jump to M74 before it gets too low. And here is M74, and you don't want the phantom galaxy to disappear on you. It's still above the murk at 24 degrees high at 7:30 p.m. And here we see its ghostly appearance at the same 60x. Here we see M45, the Pleiades, naked eye bright, well before the sky is dark enough for M77 and 74. So yeah, it probably should be first. By 11:15, you will have advanced to the 3 galaxies under the belly of Leo, a little over 2 degrees under the halfway point between Regulus and Scherten. With low magnification, it might be possible to spot Messier's 95, 96, and 105 together in the eyepiece, 3 at once. But if they are too faint to be seen, and if you need to jump to higher magnification to boost contrast, simply drop in the higher eyepiece and you can scan slightly to the southwest to find M95. And once you have it centered and you confirm it and you mark it off on your list, then you can slew to the east, and there's M96. Once you have it centered, recorded on your book, then you can slew slightly northeast. And if you do, you will pick up M105. If you see other galaxies with it, M105 is the brightest one. You can then repeat this exercise to find M65 and M66 before moving on. By 11:15 or so, you will have reached the Coma cluster of galaxies where there are 16 Messiers waiting to be found. Problem is, there are over 2,000 galaxies in the cluster, hundreds of which are NGC objects intermixed with the 16 we're looking for. Now, as you hunt for the Messier galaxies, you will likely find more than you're looking for in the eyepiece. The Messier galaxies are probably the brighter ones. You may like to have a detailed star chart of the Coma cluster to help you identify the Messiers, and maybe practicing with the planetarium program beforehand may help as well. And here's the scene in the southeast shortly before dawn as the summertime Messiers rise into view. Many of the final targets are grouped in the same constellation, which may help you out. Scorpius has 4. Ophiuchus has 7. There are 15 in Sagittarius alone, and 8 up north in Ursa Major. From Toronto at latitude 44 degrees, the open cluster M30, last on your list, lit rises with the sun only 5 degrees below the horizon. So atmospheric extinction with the cluster so low will reduce it to magnitude 12, and the civil twilight will simply wash it out. You will need to wait until the next new moon in April, which is also a Messier opportunity, to maybe catch this cluster, or simply wait until the summer when it's an easy find if you're not in a hurry. And that's all I've got for tonight. So are there any questions?
Any questions in the room? Okay, let me grab the microphone.
What do we do if it's cloudy?
For some events, you can catch it online, or you hit the road.
What if I don't drive?
I'm thinking of hitting the road for the eclipse if necessary.
Didn't seem to be a satisfactory answer, but I don't know. Any more questions?
I'll curse if it's cloudy. How's that?
So I was looking at your description of, or the explanation of the aurora and the solar winds, and I guess I have a question. If you live in the far north, are you exposed to more radiation during aurora events? It looks like the solar winds are hitting the Earth.
Our atmosphere will catch most of that. No,
Okay.
You'll simply enjoy the view. I wouldn't worry about radiation actually hitting you.
All right.
It's up there.
All right, thanks.
Yeah.
Questions in the room? No? How about online? Yes, we do have a question online.
Hi, just noting down the questions here. One question from Guy Yanez. He's from Brazil. Let me see. He was from Chile. I'm sorry.
Southern Hemisphere. That's great.
Yes.
That's fantastic.
Maybe if I can get my screen to come back up here. Give me a second. Okay. One question for you that are planning to be at the eclipse in April. What celestial objects will be spotted during the eclipse near the sun?
Well, we will be able to see Jupiter and Venus. The Pleiades will be bright enough, I believe. And as I showed in the show, with any luck, ponds, brooks will definitely be a spectacle with the sun eclipsed next door. It should be great.
Okay.
Did that answer the question? Oh, what else might be visible?
Yeah.
There might be a handful of very bright stars. I didn't really investigate deeply to see how many. Where might Orion be? Would Sirius be up that time? I'm not sure.
Okay. I can't answer that either. Comment from Ali K. Arnold, thanks for the excellent and very informative presentation. Among other things, I very much enjoyed the way you integrated graphics into your presentation.
Oh, thank you, Ali. Yes, thank you. I don't like word slides.
And Zapfan said, if it's cloudy, maybe rent a plane.
Yeah. I do have a travel trailer, so I'm going to have it out of storage and ready to hit the road. If, like, you don't want to go to Niagara Falls, it's going to be a zoo because the center line goes right there. Imagine Niagara Falls is going to be a mob scene in Buffalo as well. And if I want to cross the border and get down to somewhere further south, I have to time when I'm going to do that. So It's going to be interesting. The other option is to go further east towards Kingston and in that area.
Okay, any more questions? Yes, we have one here.
Hi, great presentation. Will you be posting these slides online so we can refer back to them?
Well, I'll do something in that regard.
Yeah, I'd really like to see the graphic of the eclipse with the Pleiades and the planets and the comet,
Yeah.
so I know exactly where to look. And
Yeah, I cobbled that picture together by getting an image in stellarium of the comet by closing in on it, then get that image of the solar eclipse and drop it in and shrink it down and position it where it ought to be. And I'm hoping that I actually see them. That would be awesome. Fantastic.
Okay, very good. No more questions
All
then.
right. Well, thank you.
Well, thank you again, Arnold. We are going to take a short break and switch over to the next presenter's computer. Okay. All right, so welcome back. Our next speaker is Arushi Nath, and she'll talk to us about integrating sparse and dense photometry methods for improved asteroid property analysis. Come on up, Arushi.
Thank you. Hello, everyone. It's great to be back in person at the Ontario Science Centre. My name is Arushi, and I'm a grade 9 student. Today, I'll be talking about a project I made where I combined sparse photometry with dense photometry to learn more about asteroids. So it's really impressive to say that even up to this day, we're still discovering hundreds of near-Earth asteroids every month. Just last month, more than 180 asteroids were discovered. And we've started to get better with tracking these asteroids, detecting dimmer asteroids, and we've even started to get better with detecting asteroids before they impact with the Earth. For example, in January of this year, there was a small 1 meter asteroid which was about to impact the Earth. Of course, these are small asteroids, so they don't cause harm, and most of them burn up in the atmosphere. But we've started to be able to detect them before they actually impact. Actually, a citizen scientist, Christian, from Hungary, was the one who discovered the asteroid just 3 hours before it entered the atmosphere. And this was only the 8th asteroid to have been discovered before. And since we've gotten so good at tracking these asteroids, we were actually able to find exactly where it would land as different citizen scientists across the world started tracking the asteroids. And we were able to find the meteorite of the asteroid, which was pretty cool. And this is actually what my project is all about. What I'll be talking about is how to learn more about these asteroids. Because let's say we're not able to find a meteorite when it enters the Earth, or what if everything burns up in the atmosphere? How can we still learn about the physical properties of these asteroids? So I'll start off by talking about a very simple concept. It's called the phase angle. So this is simply the angle between you, the observer, the asteroid, and the sun. And this angle tells a lot about the asteroid. And you could be standing anywhere. You could be on the Earth, you could be on a spacecraft. And the interesting thing about this is, let's say the observer is on the Earth. We know that the Earth is always orbiting around the sun, which causes changes to the phase angle. But at the same time, the asteroid is also orbiting around the sun, which causes even more changes. So what can this phase angle actually tell us? Well, as the phase angle comes closer to zero, we observe what is called the opposition. And I'm going to show you a short video which actually explains what happens during the opposition. So what you will see here is a moon of Mars called Phobos, and this is a video that's been taken from a Mars orbiter, and you will see what happens to the asteroid as it comes closer to opposition. So really look for what changes you can find. And on the right of this, you will also see basically how the phase angle is changing, so you can match it with what you see. So you can see the asteroid is slowly coming closer, the phase angle is slowly becoming smaller. And you can see that the asteroid, there was a huge surge in the brightness as it came right at the zero phase angle. And you can see as the phase angle is becoming bigger again, the asteroid starts to become dimmer. So let me just go to the next slide here. Perfect. So what exactly was what you just saw? So you saw a huge surge in the brightness of this moon right during the opposition. And this is caused by two different effects. One is the shadow's disappearance. So of course, this is an object, there's many bumps, there's many craters, and these cause shadows on the surface of the asteroid. But when the sun is directly behind the asteroid, then the shadows will disappear, causing a huge increase in the brightness of the asteroid. At the same time, most of these asteroids have very rough surfaces, which causes the light to scatter as it reflects off the asteroid. And when sometimes when this light scatters, it basically interferes constructively, causing an actual increase in the brightness of the asteroid. So, what exactly is this surge? So this surge can be observed via what we call the phase curve. And this is a curve where if you plot the phase angle on the x-axis and the reduced magnitude on the y-axis. So what is the reduced magnitude? This is simply the magnitude of the asteroid with all other changes accounted for, like changes in heliocentric distance, changes in geocentric distance. So the only change in the brightness that you're observing is because of the phase angle. So you can see between the phase angles of 0 and 5, there is that brightness surge that's very obviously visible. And this is what we call, basically the surge in brightness is measured by what we call the slope parameter. And this slope parameter is very important for determining physical properties of the asteroids, which I'll talk about a bit later. And one thing that this phase curve also gives is if you look at the zero phase angle, whatever brightness reduced magnitude value you will see there actually refers to the absolute magnitude of the asteroid, because absolute magnitude is simply when there's a 0 phase angle and where unity distances have already been accounted for. But after the 5-degree phase angle, from 5 to 25 degrees roughly, you will see that the line becomes relatively linear. And this is what we call the phase coefficient. And this is where basically the line becomes linear. And this can also give additional physical properties about the asteroid. So how exactly do we use this phase curve to find the physical properties? Well, the first thing is absolute magnitude, which I just talked about. So this is where the phase angle is 0, and there's a simple formula we can use, which uses the reduced magnitude to basically find this absolute magnitude. And the important thing it uses is the g, or the slope parameter, which I just talked about before. Second, to find the geometric albedo, this is where you use the linear slope that you see after. And one thing to note about this linear slope is that it can only be accurately determined once you have an accurate g slope. And this really causes us to think that we really need these important phase angles, these smaller phase angles of 0 to 5 degrees, to be able to accurately determine the whole phase curve. And finally, we can also determine the size from this phase curve just using the absolute magnitude and geometric albedo. So here the problem comes along, because mostly you think of using dense observations, like just taking observations from your own telescope to be able to observe this asteroid and find its magnitude. But the thing with this is, while these time series measurements are very good for like finding rotation period of the asteroid, orbital period of the asteroid, where all of these clumps of data is really necessary, it doesn't really help us with the phase curve, because in the phase curve, you need observations of the asteroid at different phase angles, which dense photometry simply does not give. So that's where I turn to sparse photometry. So this is taken from sky surveys, and this is basically time series data, but it's not continuous. So maybe one observation every couple of months. And the good thing is with this is we get to explore all the different phase angles of the asteroid. So by combining dense and sparse photometry, we would be able to get all of the physical properties of this asteroid. So how did I go about getting sparse photometry? Well, for here, I used sky surveys. So one of the ones I used is the Gaia sky survey, and that's just Gaia is a spacecraft that's always orbiting around. And this Gaia Space Telescope has 2 telescopes, and it takes its measurements in the G magnitude. And this telescope is very good, and it gives us a huge range of phase angles, from 10 degrees all the way to 30 degrees. But as I mentioned before, we also need the small phase angles. So while this is great for the linear part, we would also need more for the beginning part. So to get these Gaia observations, I simply used their database, where I was able to basically get the MPC code of the asteroid. And for each MPC code, I was able to get the date the observation was taken, as well as the magnitude I was getting and the magnitude error. So this would allow me to give me all the parameters I would need to get the magnitude and create a phase curve. So how many observations does Gaia take of each asteroid? This is where the problem comes along, because you can see as not many asteroids have more than 50 or 60 observations. And even below, it's slightly more rare. And the thing is, we need a lot of observations to create a phase curve. So I used a second sky survey. This is the Atlas Sky Survey. So this is a ground-based telescope, and it's a 0.5 meter aperture telescope, so slightly smaller. But the good thing about this is it observes all phase angles, so the small phase angles as well as the big phase angles, which is exactly what we need. So to do this, I used the Atlas forced photometry pipeline, which I could input the MPC code I wanted or the asteroid I wanted, and it would give me all of the time series magnitudes that it had collected of this asteroid. And finally, I used the Zwicky Transient Facility, or ZTF telescope, and this is another ground telescope, and it actually scans the whole northern hemisphere every 2 days. And the great thing about this telescope is, once again, it gave all phase angles, which was perfect because it would allow me to get everything I needed. So once I had all of these sparse observations, I decided to combine them with dense observations. So in particular, I was looking at a specific asteroid in this case called Didymos. Many of you guys must have heard in 2022, NASA launched its mission, its Double Asteroid Redirection Test mission, which was aimed at crashing into the moonlet of this asteroid to basically for a planetary defense test, because their goal was to change the orbital period. And I thought, why not use this asteroid as a test? So I collected sparse observations. In this case, I used the ZTF telescope. It's important to note that this asteroid was unfortunately too faint to be observed by the Gaia sky-based survey. And in addition, I got a few observations from the Asteroid Light Curve database, or ALCDEF, and this would give me the dense observations I need. So here you can see is the phase curve of Didymos. So it's from about 3 degrees to 20 degrees when talking about phase angle. And you can see that the triangle shapes here are all the sparse readings I've got, and the circles are all the dense readings I've got. And this allowed me to create the phase curve and basically allowed me to get the H and G values. So these were very important physical properties I was able to get, and it allowed me to get many parameters. First, I was able to find the absolute magnitude of Didymos using the formula I earlier mentioned, and I found it to be 18.14 magnitude. And this was using the G, so the opposition part of the curve. Second, I was able to find the geometric albedo of Didymos. This was using the linear part of the curve, so from about 5 to 20 degrees. And I found the geometric albedo to be 0.14. Then finally, using both the absolute magnitude and the geometric albedo of the asteroid, I was able to determine the size of Didymos, and I found it to be 840 meters in diameter. But this geometric albedo is very interesting because geometric albedo, as you probably know, is basically shows how reflective the asteroid is on a scale from 0 to 1. But this is not all it gives. It can also give so many more physical properties about the asteroid. In particular, I was looking at the composition because different types of asteroids with different compositions have different geometric albedo ranges. For example, asteroids who are carbonaceous will have a very low geometric albedo because they don't reflect much light, and this is normally below 0.1. Whereas metallic asteroids and silicate asteroids will have a higher geometric albedo as they reflect more light. So using this geometric albedo, I would be able to find the composition of the asteroid. So, knowing the albedo of Didymos was 0.14, I concluded that it was either S-type asteroid or an M-type asteroid. And as you can see on the right, this is an image from the Draco camera of the asteroid Didymos, and you can see that it definitely looks stony type, concluding that these results were correct. Next up, I'm going to talk about a different part. Now that I had the absolute magnitude, I had the albedo, I had everything else, what else could I get from the asteroid? So here I turned to the Lowell Minor Planet Services, where I was able to get the ephemerides of the asteroid. And this would be very useful for the next step, finding the rotation period of the asteroid. And this actually requires the G value of the asteroid that we calculated before. This would allow us to count for all types of offsets. The unity offsets, so the distance from the Earth, the distance from the Sun, as well as the phase angle. And this would allow us to basically turn from asteroid light curves where the change in brightness could be due to several reasons, and actually give us light curves where the change in brightness was only due to the actual physical properties of the asteroid. And once we had this, then I could determine parameters like the rotation period of the asteroid. Because as asteroids rotate, they're irregular in shape for the most part. So their light curve produces 2 maximas and 2 minimas. And using my algorithm, I would be able to combine sparse photometry and dense photometry to basically combine these light curves and find the rotation period. And if the asteroid had a moonlet, as was the case with Didymos, I could simply subtract the rotation period from the main light curve, and then I would get information about the orbit of the moonlet. And I was able to find the rotation period to be 2.26 hours, and I was also able to find the orbital period. And actually, after NASA's DART impact, the orbital period of this asteroid reduced by 35 minutes, proving that the deflection was successful. And all my results were validated with external sources like NASA, and they validated very closely. And this proved that merging sparse photometry with dense photometry does give very accurate results for Didymos. And this is not yet over. I'm starting to expand my algorithm to work on several other asteroids. For example, here you can see the phase curves I constructed for 3 other asteroids: Eurybates, Themis, and Nyssa. And this is all done using multiple sparse datasets like Gaia, ZTF, Atlas, and then also combining them with dense photometry datasets like the Asteroid Light Curve database, so I could get the maximum physical properties possible. And you can see here I was able to find the albedo of these asteroids as well as their type or composition. And another thing I would like to do in the future is expand my photometry algorithms to find the composition, but find the composition more accurately. And how would I do that? This is using observations in multiple filters or multiple wavelengths. And this will require as well both dense and sparse photometry, because different sparse surveys give the magnitude of different asteroids in different filters. And using my own dense observations or dense observations from databases, I can also find the asteroid in different filters. And this would allow me to find the composition. So you can see here, this is a preliminary analysis I've done with the 211 Isolda asteroid. And I was able to take the observations in 4 filters, R, G, B, and I, in the Johnson's filters, and calculate the absolute magnitude for each of the wavelengths. So more analysis on that to come up. And finally, I'm still looking to expand my algorithm to many more asteroids. In particular, I'm very interested in the near approach asteroids, so asteroids who are about to come very close to the Earth. And if anyone is interested, or if you know anyone who's interested in observing some of these asteroids, please let me know, because I'm always looking for observations of these near Earth asteroids who are approaching. And I would like to finish off by sharing some outreach I've been doing in the past couple of months. Just last month in February, for the International Women in Science Day, I got to present to so many youths and parents and women about the importance of science and share a bit of my journey. In addition, I got to talk about the Royal Astronomical Society of Canada and how it shaped my interest for astronomy. In addition, just a few days ago, I was out in to talk about RASC at the Save the Ontario Place rally, which was held in Lynn Park. And in addition, a few months ago in December, I got the chance to speak to youth from all around the world, over 2,000 kids. And there I got to share my science journey and also mention the Royal Astronomical Society of Canada and all of the times I visited the observatory. So with that, thank you so much. I'd be happy to answer any questions.
Thank you very much, Arushi. Very impressive, as always. Well done.
Thank you.
We have one question here in the room.
Thank you. I noticed that most of your phase angles go to about 20 degrees. Might there be something interesting with phase angles greater than 20 degrees?
Yeah, well, phase angle 0 to 20 degrees is actually what gives the most important information. And after 20 degrees, there's not too many physical properties you can get.
Okay, any more questions in the room? Yes, oh, sorry. You go.
Is it true that Oumuamua had something to do with aliens?
Could you repeat that question?
Is it true that Oumuamua, the interstellar asteroid that passed us in 2017, they were doing similar measurements of brightness? What is your opinion on it?
I don't know too much about it, so I can't give an answer, but I'll definitely look into it and I can let you know later on.
All right, thank you.
Question over here.
Hi, great presentation. One question: when you like analyze the wavelength of the asteroid, do you just get it like it's an S type, it's a C type, or you can know more about the composition?
Yeah, for sure. When you observe in multiple wavelengths, you're basically able to see how the brightness of the asteroid changes across wavelengths, which does give you information mainly about the composition. I don't believe there's anything else you can find from it, um, uh, at least to my knowledge, but maybe there is. But from what I can say, no.
Are you a grade 9 student?
Yes.
Okay, wow. I just thought that was maybe an old slide. That's amazing.
Thank you so much.
And we have one question online.
Bloor Collegiate. It's yeah.
We have one question online. It's do you need to determine the shape of the asteroid to estimate the rotational period? That's from Guy Yanas.
Oh, that's a great question. And actually, you do not. To find the rotation period, all you need is the light curves of the asteroid. And once you determine the light curves, actually the amplitude of these light curves will give you information about how irregular this asteroid is, which can give you information about the shape. And but once you have the light curves, what you can do is you can take all of your light curves together and then combine them. What I did is I used a process which used root mean square error and congruent modulo, and where I was able to basically try fitting the light curves from periods 2 hours to let's say 10 hours, and then I found the one with the smallest root mean square error, and that gave me the rotation period. And while finding the shape of an asteroid is definitely a very interesting physical property that I would love to look into in the future, you do not need it for rotation period.
Any more questions in the room? None. Okay, well, thank you again, Arushi.
Thank you.
Great presentation. We're going to take a short break while we get ready for our next speaker. Hello and welcome back. Our next speaker is Michael Watson, and he'll talk to us about how to photograph a solar eclipse. Take it away, Michael.
Okay, well, thank you. It's a pleasure to be back speaking with the Toronto Centre. Last time I was here was at the end of last year in December, and I talked about having done a solo driving trip to Texas over the course of 5 days to observe and photograph the annular eclipse of the sun. And so rumor has it that we have another eclipse of the sun coming up in about 32 days. And so I thought that I would have a little discussion about photographing solar eclipses. Now, many of you have seen solar eclipses. Some of you will have seen total solar eclipses, and you may be very familiar with what I'm going to be talking about. But there may be some things that you haven't necessarily experienced yourself or thought about. And so I'm just going to get right to it. It's the last presentation of the night, and I've got a lot of stuff to show. So let's just start here then with the presentation. And so, as I say, a lot of this you may know already, and you may have experienced. What I would like to do is mention, and this is, I think, a really important guide. The work by Alan Dyer, who is one of Canada's and indeed the world's greatest astrophotographers, a member of the RESC Edmonton Centre. And this is a book that is available in e-format or PDF, and it gives you really everything that you need to know, and probably more than that. So that's a very, very good resource. So most people in photographing an eclipse of the sun, and I'm talking about now here either partial or total, because I'm going to be talking about both of them, because not everybody's going to be traveling into the path of totality. Most people are going to be using a DSLR or a mirrorless camera. And so what we're talking about is a 35 millimeter or a cropped frame camera. And so that's what I'm going to be talking about here. And we have to recognize and understand the crop factor. And so we have here, here's a diagram of various relative sizes of sensors in cameras that are attached to telescopes or lenses. And we have, for example, if you, I don't know whether you can see my cursor, hope you can. On the left side, we have 1.0. This is a 35 millimeter full frame camera, so-called full frame. They came out several years ago. Before that, the sensors were much smaller, and they were so-called crop frames, and they have a much smaller field of view. And you see the various sizes of crop frames here, generally about 2/3 the size in both dimensions of a full frame camera. And that has a significant effect on the field of view and the apparent size of the eclipsed, well, of the sun or the moon or the eclipsed sun when you take your photographs. And so in order to get the effective focal length of your lens, you have to multiply the actual focal length. That is 50 millimeters, wide angle 35 millimeters or 24 millimeters, telephoto 85, 135, 200 as the case may be, by that factor on the left. And so the smaller the size of your sensor in your camera, for example, a crop frame camera, the more you have to multiply it in order to get the effective focal length. So a 50 millimeter lens, for example, becomes something in the order of between 85 and 105 millimeters. In other words, a short telephoto lens. This is a really important aspect to understand about photography. Right? So that's the effective focal length. And so what we see here is then just in relative size, the full frame border and the crop frame border. And let me show you, it's sometimes not completely understood how small the sun and the moon actually are. They subtend an angle of only half a degree in our sky. And so if you were taking a photograph, for example, of the eclipsed sun or just of the moon, or the sun not eclipsed with a solar filter, this is the size that you would get with a 50 millimeter lens. It's really tiny. If you go to a wide angle lens, for example, 35 millimeters, that's what you would get. A 24 super wide angle lens, that's what you would get. You have to go to a telephoto lens to get the image size large enough to get any kind of detail, for example, in the corona. And so that's with a 135 millimeter lens. We go to a 200 millimeter lens. I use a 200 millimeter lens a lot in my astrophotography, including deep sky astrophotography. You go higher, up to 500 millimeters. That's the size you're going to get. And so just look at that. If you have a cropped frame camera, then just think about the reddish outline there and the size of the eclipsed sun. That's what you're going to get with a 500 millimeter lens. With a full frame camera, It's obviously going to be much smaller in comparison, although the number of pixels in both dimensions will be greater. Then we go up to a 750 millimeter lens, 1200. This is approximately the focal length that I use for solar eclipses with my 1253 millimeter Explorer scientific 152 millimeter telescope, and you'll see some pictures taken of that. So this gives you an idea of the telephoto lens that you are probably going to need if you're going to be in the path of totality and want to get any detail in the corona, and 1600 millimeters and 2000 and so on. Okay, so let's go on. Let's just talk now about solar filters. Obviously extremely important. I think that many people, most people maybe will be familiar with this, and that is the Kendrick filters. Take a look at what it says in the upper left there. They're not accepting any orders anymore. And anytime you get close to any solar eclipse, filter manufacturers really sell out. The Kendrick filters are wonderful. I have used them for years. They're really terrific. They are full aperture filters, which go right on the front of the telescope. They're manufactured in different sizes. And here you can see the Kendrick filter on the front end of my Explorer 6-inch or 152 millimeter f8 refracting telescope, which I've used for solar eclipses for a long time. And so this is what the sun then looks like through a Kendrick solar filter. And you may be thinking, well, whoa, wait a minute, it's white, the sun's yellow. No, it's not. Most solar filters actually have color in them. This is the actual color of the sun, because the Kendrick solar filter does not filter out any particular rays of sun. It really is a neutral density filter that filters out the infrared. And so that's what it actually looks like. And you can see there the sunspots, and you can get some pretty good detail through a filter such as this. This was at last October's annular eclipse in Texas that I observed. And so now, this is one thing that's really important. How do you focus in the day, in daylight? Well, what I always do is I'm using the filter on the front of my telescope, obviously, put a little hood over my head in order to be able to look at the viewing screen on the camera, and then I focus on the sunspots or on the limb, on the edge. And so here, that's not too bad a focus, and that's what I'm going to use to focus. And then you lock the focus, and you can use that as soon for the total phase. Just take the filter off, because there is no change that you have to make. The image plane is exactly the same with the filter on or the filter off. So that's how you go about focusing, and you can do that with a telephoto lens as well. A lot of cameras now allow you on the screen to zoom in, and so you can zoom in on a filter, on a sunspot rather, and then focus using the fine focusing ring on your or focusing mount on your telescope, or obviously the focusing ring on your camera, and then lock that down. Now, you don't always need a filter, and so I'm just going to show you some photographs. And this is particularly if the sun is low in the sky. That's not going to be the case for this eclipse for most of North America. It's going to be quite high in the sky. We'll talk about that in a little bit. But if the sun is low in the sky, you can actually shoot without a solar filter. I'm going to show you this. But also, if there is cloud, and there is bound to be cloud, it's April. It's going to be not a terribly advantageous month for weather through almost all of the eclipse path, except in Mexico, unfortunately, about 100 kilometers inside the Mexican border. We had talked for a long time about going into Mexico, but I just don't feel like taking, a lot of valuable equipment across the border and trying to get across the border on the morning of the eclipse. So we're going to be watching from Texas, and unfortunately, as soon as you cross the border into the U.S., the weather prospects are really diminished down to about 60% chance of clear skies in Texas, all the way up to somewhere in the neighborhood of 45 to 50% on the south shore of Lake Erie, and then less as we go east across Lake Ontario and into eastern Canada. But you may be able to catch a glimpse of at least the partially eclipsed sun through cloud, in which case you may not need a filter at all. So here is an example of a solar eclipse right near, obviously, sunset in October of 2014. I shot this with a 400 millimeter lens. Yes, 400 millimeter lens. And here you can see no filter whatsoever. Nice pictorial view. ISO 100 with a 1/2000 second exposure at f/22. And so obviously you're going to be stopping way down and you're going to bracket your exposures. And you may get something that is fairly dramatic, something like this. Another example. This was a very early morning eclipse in November of 2013 from the North Shore of Lake Ontario in Western Toronto, right on the shore. And again, great dramatic cloud effect. And this was through my Explorer 6-inch telescope. Again, one ISO 100 and shot this time at 1/8000th of a second, because of course the telescope has a fixed focal ratio, and that is f8 in this photo. So you can do a lot of experimentation and come up with something that's pretty interesting. Oh, oh, hope you can hear me again. All right. This was the annular solar eclipse of 3 years ago, which was annular over Hudson Bay, but it was a very interesting early morning sunrise partial eclipse as seen from the North Shore of Lake Ontario. And here again, same telescope. And I shot this using ISO 400, and you'll see the exposures there. So you can actually do some really interesting work without a solar filter at all. Now, this is what everybody wants, and you're not going to be writing all of this down, but you can get it afterwards in the replay on YouTube. And the so-called proper exposure for various phases of the eclipse. There is no such thing. It's all a matter of personal perception, and it depends on a lot of factors, and I've listed 2 or 3 of them here. And the last one at the bottom here of this screen, I think, is really important. And you don't hear people talking about this very often, but it's something that I have noticed and determined and discovered over the decades that I've been doing this. Focal length. There's a psychological effect. If you have a very, very large frame, which is black, and then a very small, tiny little eclipse sun with some corona there, in order to make any kind of visual impression, you actually need to increase the exposure so that the corona expands outward from this black hole. Whereas if you're using a very long focal length and the black hole of the moon obscuring the sun is very large on the frame, you can easily get a very dramatic photograph by having a much shorter exposure, and you don't get nearly as much corona. There's a real psychological effect to this that I have seen. But again, what you're going to do is you're going to bracket your exposures significantly during the period of totality, remembering that this eclipse is about 2/3 longer than the great August 2017 eclipse. So you got a little bit more time. So this is courtesy of Alan Dyer, and these exposures, I think, it's all very psychological and very subjective, but these exposures, I think, are just about dead on for the images that I like when I produce them myself. All right, and another one from the great astrophotographer Jerry Lodrigus in the U.S., not quite as well known here in Canada, very well known deep sky astrophotographer, but also an eclipse astrophotographer. So look up his website, and this information is all free. And this gives you the exposures that you will use, remembering that with a telescope, you've got a fixed focal ratio, f5.2, f8, f10, as the case may be. With a camera lens, you have an infinite variety from, say, f2.8 all the way up to f22 or even f32. And so you can choose your exposure, you can choose your ISO setting, you can choose your exposure, and you can choose your focal ratio or f-stop in order to get the appropriate combination that will produce the exposure that you like. Okay, what's really important if you're not using a telescope and you are using just a camera with a telephoto lens, you got to have a strong, steady tripod. This is absolutely critical. More photographs are ruined by flimsy tripods than anything else. It's easy to buy a good camera, easy to buy a nice telephoto lens, but what you really need to spend some money on is a tripod. This is the one I use. It's a Manfrotto. I really like this one a lot. I know they're very expensive, but they're really fantastic. And I've been using this now for decades. And you see here a camera with a 200 millimeter lens with a very heavy-duty ball and socket head on the top that allows me to point the camera in any direction that I want. And so at this eclipse, this is going to be really important to appreciate. At this eclipse, the sun's going to be really quite high, even though it's only April. In Texas, where we plan to be, it's going to be 2/3 of the way, more than 2/3 of the way from the horizon to the zenith. So that's going to have your camera pointing way up. Even from Toronto, the elevation is going to be at 45 degrees, almost exactly halfway from the horizon to the zenith. You have to think about that. You got to plan it. You got to set up your camera and your tripod ahead of time. Set it using an inclinometer that you can buy for about $15 from Canadian Tire. Set it for the actual elevation or altitude above the horizon, and then figure out, are you going to be able to get down to your camera to be able to see, to be able to photograph, to be able to frame, to be able to focus. You got to practice ahead of time and think about all of these things. If you do, you'll get great photos. If you don't, you may not. Also consider using a right angle viewfinder as well for high elevation. And a lot of cameras now, of course, have tilting viewfinders or screens on the back of them. Most mirrorless cameras have that as well. The Nikon Z7 that I use has one. And those are really, really helpful because you can then focus looking down rather than trying to crane your neck and get under your tripod to look straight up. So these are really important things. Now, you can get some really interesting super wide angle stuff with 50mm or 24mm lens. Earlier, we were hearing about the location of various planets and so on. At this eclipse, I can tell you, because the sun is going to be located in the constellation Pisces, there are no bright stars in the region at all, as compared with 2017. The August 2017 eclipse, the first magnitude star Regulus was located just outside the sun's corona. It was a great opportunity, and I'm going to show you a photo of that a little bit later. We don't have that for this eclipse. However, we do have Mercury, which unfortunately is going to be very faint, magnitude 4.8 at that time. We have, and this is, by the way, horizon is seen from Toronto, so we're sort of looking straight up to the south. You're not going to see that corona because, of course, Toronto is outside the path of totality. But we see Venus there, magnitude minus 3.9, fairly bright, not nearly its brightest, but still fairly bright. And then we get Neptune. No one's ever going to see that. And then the brightest stars that are in the vicinity are all fourth magnitude. I don't think that there is a chance, well, certainly no chance of seeing them, and probably no chance actually even of photographing them, although I'm going to try. Now, this is the framing that you could do with a full frame camera with a 35mm lens. If you have something like that, you will be able to get Mercury and the sun and Venus in the same frame. Now, I should also point out that the brilliant planet Jupiter that Arnold was talking about before is to the outside the frame to the left, about the same distance away from the eclipsed sun as Venus is to the right. All right, and so if you if you want to use a 24mm lens on a full frame camera, you might possibly be able to get Jupiter, the eclipsed sun, and Venus all in the same frame. Now, this is something that people don't often do, so let's just talk about that for a minute. Back in 2017, this is what we did. You can take binoculars and you can project the partially eclipsed sun. It looks like a couple of eyes almost closed. And this is really fun and really interesting. In effect, the binoculars are kind of pinhole cameras in a way, but also you don't need binoculars. At this past October's eclipse, when I was in Texas, I turned around and looked down, and no one else was doing that because I knew what I was going to see. There were leaves on the trees, and this is what I saw. Dozens of little eclipses through the leaves, which acted as little pinhole cameras. So there are things that you can see as well and do nice little pictorial views to give a different impression and a different view of this of the eclipse coming up. But watch out for the technology. I really do like this. People talk, setting all of this stuff up and then wasting the 4 minutes, 30 seconds of totality because their equipment doesn't work or their computer algorithms don't work. And similarly here, an eclipse is something to be enjoyed and wondered at. But I've also found, and a lot of people, very experienced people, don't do any photography at all because they just want to watch. I love later on in the years later looking at the photographs, because it all brings it back to me. You're going to have to decide yourself. Okay, a few tips. All right, some of these are really obvious, but you can't be doing it the morning of the eclipse, and you can't be doing it during totality. You know you'll mess it up. Remember that. Auto flash should be illegal. All right, manual settings. Do not use auto settings and disable the autofocus. You have to focus manually because your camera just will not be able to figure out how to focus on what it is seeing. Right, so these are just a few things that you can use. Let me then now go to the 2017 eclipse to give you an idea of what you can possibly get, particularly if you're using a telescope. And this is the first of the great American eclipses, as I think you remember, the first two, August 21 of 2017. It was an entirely North American total eclipse. I think probably the most widely observed total solar eclipse ever in history to that point in time, although this one is clearly going to be more well observed, more people traveling, partly because it's through the eastern US, and partly because it's now 7 years later. And so this was a trip that I took with my family over 5 days. As you can see here, our main observing site was going to be in Grand Island, Nebraska. The morning of the eclipse, about 2 in the morning, I took a look at the weather forecast. It didn't seem to be, it seemed to be a little doubtful for Grand Island, so we put all our gear in our car, and on eclipse morning we drove over 500 kilometers to western Nebraska. Some of you have seen these photographs before, and it was foggy the entire way, but just as we got to Scotts Bluff in western Nebraska, it cleared up. The sun burned off the fog, and we got the clearest of the total solar eclipses that I have seen, starting in 1972 and all the way through to 2017. So here's my gear set up for this eclipse. It was just a tremendous time. And what I'm going to show you here then is what you can get with a decent telescope, pretty good telescope, but you don't have to have one telescope that's that big, using a good solar filter. And so here we see sunspots with the advancing limb of the moon. You can actually see with careful focus mountains on the edge on the advancing limb of the moon. And so this was through the solar filter, and you'll see then the focal length and the ISO that I was shooting at. I generally like to use somewhere in around 200 for an eclipse. I can go down to 100, but I like to use 200. And then you'll see what the exposures are, but you're going to be bracketing them. Now, one of the things I'm going to suggest is this. You got to do a bunch of practices, and what I always do is I take photos of the uneclipsed sun an hour or so before the eclipse, and I test out different exposures. And what you want to get is an exposure that actually does show the sunspots, but actually shows a little bit of dimming as you get to the edge or the limb of the moon, because that's then, if you get that, then you're not overexposing. Because the sun is, not surprisingly, I think we all know, visually dimmer at the edge because the light has to go through more of the sun atmosphere and all of those things. And so you really should try to practice that. And that then will give you what you consider to be the right exposure and will also allow you to get the sunspots rather than having the sunspots burned in and really invisible in your photos. So I think that that's really important. So we get here the diamond ring both before and after with prominences, as you can see. And so this, and obviously, of course, no filter. So this will give you an idea of what I was shooting at. Here for the diamond ring, ISO 200 and 1/3200th of a second. So these are short exposures that are required in order to get the diamond ring. Also appropriately to shoot the prominences, and you can get some very, very inner corona using this kind of exposure as well. And then this is my favorite photo, obviously sort of full corona. And, processing it properly, you really get the brushes and the detail in the corona. And so that is the exposure, straight up, ISO 200 and 1/80th of a second. Now, use shutter delay mode. Lock your mirror if you're using a DSLR. Lock your mirror up if you're using a mirrorless camera. You don't have to worry about that. But what you're trying to do is eliminate or minimize vibration. And if you're concerned about your mount, and for example, if it's windy and your mount's blowing around a little bit, then increase the ISO even up to 1,000 so that you can then increase the sensitivity and then shoot a much faster shutter speed of 1/2000th of a second, for example, so that you will eliminate any vibration. Camera sensors now are so good that even at high ISO settings, you're not going to get pixelation or graininess. They really are very good. So that's just a little bit of a tip there. This was what I wanted to tell you about. That is Regulus in the upper left, and I really wanted to photograph this one. And again, I just moved the telescope off center to be able to shoot this. Slightly longer exposure because I didn't know how the long exposure I would need actually to get Regulus, but I was able to get that, and you don't see that very often at solar eclipses. And then finally, this is one of my favorites of prominences, just toward the at the end of the eclipse, and here shooting much faster because I didn't want to get if you shoot at a slower shutter speed, then you're going to completely burn in the prominences and you won't get them at all. And I can tell you that is not fake coloring at all. That is what they look like. That's the color. You look at these prominences visually, that's what you see. And the camera can really reproduce quite well exactly what you're going to see visually. So it's pretty impressive when you see something like that. This is something you don't see very often. I decided that I would try to shoot a very, very long exposure, well, fairly long exposure during the eclipse to see whether there was any way I could get Earth shine. And of course, what you're seeing there in the white is the completely burned in corona around the eclipsed sun. And actually, I was able to get Earthshine at its brightest. Obviously, Earthshine is at its brightest at new moon, but you can't see it because the sun's in the way and blocking everything out. And so this then was again shot at ISO 200, but I shot it at 1 2/3 seconds at f8, and that's what I was able to get. I'm going to try that again this time. I think it was Dennis DeChico who did something like this decades ago. I haven't seen one since, but I decided to try this in 2017. And then I just want to spend a little bit of time on this. We often hear, and of course you got to be careful. You have to be careful with your eyes. There's no doubt about it. I always take my solar filter off between 20 and 30 seconds before the start of totality. Always. And this one actually happens to be after the end of totality, but it was 39 seconds after the end of totality. By that time, the trailing edge of the moon's shadow was approximately between 20 and 25 kilometers to the east of us, having passed over to the east of us in Nebraska. In this photograph, you can see, the brilliant emerging crescent of the sun, but you can still see corona and you can still see prominences. And you can photograph them using a focal length like this. You might be able to get something like this with a 500 millimeter lens as well. The point I want to make is this. At this coming eclipse for people in Toronto, as we know, the path of totality crosses Lake Ontario and just the northern limit just misses Toronto. But it just misses the islands of Toronto by only about 5 or 6 kilometers. From the Ontario Science Centre, the northern edge of the northern limit is 13 kilometers away. If I was able to shoot this into clear sky from Nebraska with the shadow 20 kilometers away, you will be able to get this using a long focal length, either telescope or camera lens from the Science Centre. Let alone from parks on, much closer to the edge, to the waterfront. So you will, even if you can't travel, there's a very good chance that you can do this. I never heard anybody talk about this, and generally astronomers don't talk about actually doing photography of the corona outside the actual limits of totality itself. But you can do it. You got to be careful, sure. But remember also, for eye safety, your eye starts to deteriorate when you gaze at the sun in a fixed position for about 30 seconds. It takes about that long for the infrared light to actually do damage to your eyes. Every day we look up at the sun, we glance up at the sun, and no one says, oh my God, you're going to go blind. It takes some period of time to do that. I'm not suggesting to be careless. Be very careful. But what I'm telling you is that I have been doing this for decades. And I'm looking up at the sun, I'm looking through the telescope, I'm looking right through the telescope and on the camera, at this time. And this is what I'm seeing, and this is what I'm able to photograph. So I just want to point that out to you. There are various things that you can do and do it very safely. This, by the way, was 20 seconds after the end of totality, and this is going to be very similar to the view that you would get here in Toronto. The shadow actually happened to be to the east, and so you're here in Toronto, you're going to be to the north of the shadow, but it's the distance from the edge of the shadow that really matters. And so I actually just produced this one, processed this this afternoon when I was thinking, how about showing them what it might actually look like from Toronto through a telescope. There you go. And so this was one happy family at the end of our trip in western Nebraska. I'm finally going to just say one thing. This was supposed to be about lunar eclipses as well, but I was talking to Paul Markov, and he said, Michael, you don't have enough time, and I think he was right. But we do have a lunar eclipse coming up. It's a penumbral lunar eclipse, and most people yawn and say, oh, well, there's, it's not worthwhile. And as Arnold was saying, it's 3 a.m. I understand that. However, you can still photograph a penumbral eclipse, and it's not nothing. So what, and this penumbral eclipse happens to be visible over all of North America, as you can see here. And almost the entirety, about 96% of the moon will be in the penumbra of Earth's shadow. The southerly portion will be the darkest. And what I want to show you is the penumbral phase of a total lunar eclipse, and a photograph taken of that some time ago. And so this was in April 2014. So this was before the partial phase even started. And this is a photograph of the moon immersed completely in the penumbra of Earth's shadow. And so you actually can see a noticeable difference and a gradient from one side, the side of the moon that is furthest away from Earth's shadow, to the part that is almost touching the umbral part of the shadow. And so please do not be deterred, and don't think, oh, I'm never going to be able to photograph or even see anything. You absolutely can. And I think that this is just really, really interesting. So give that a try. And what I will say then is simply this. People say, and I think it's really true, a total eclipse of the sun is the most spectacular of all natural phenomena that it is possible for a human being to witness. And this is going to be my 10th, in addition to annular and beaded annular eclipses. There are a lot of members of the society who've seen more, many more than I have. Ralph Chu of the Toronto Centre, the world's leading eclipse eye safety expert, is one of them. But this is what we're always looking for. And I'm going to finish up there. This is just from the 2017 eclipse, a little collage. And what I'm going to remind us all of is that's the length of time until the next one. So thank you very much. I hope that that presentation will be of some use to you and of some interest. And I'm going to stop sharing my screen right now. So there we go. And again, thank you as always for inviting me. It's a pleasure to be your national president after 54 years of membership in the RASC. There we go. Thanks, Paul.
Thank you very much, Michael. Fabulous presentation, very informative, and thanks so much for presenting to us. I'm sure there's going to be lots of questions. Why don't we get started here in the room? Why am I not seeing any hands? What's going on?
It's because they knew it all. All of this is they knew already.
Here's the first question.
So speaking of filters and totality, in theory, you don't even need one, right? If you just image the totality.
Oh yeah, absolutely. No, that's completely true. Not only do you not need one, you can't use one, because the corona is sort of 1/10,000th the brightness of the sun, and so you keep a filter, a solar filter on during totality, you'll get nothing, and you won't see anything. You have to take it off.
And how do I properly time it to make sure I don't burn the sensor? Like, when do I?
Well, that's what I was trying to talk about. I was giving you an example of me photographing with no filter 39 seconds after the end of totality. And as I say, what I always do is I always take off the filter between 20 and 30 seconds before totality actually starts, and leave it on for that length of time after totality ends. Now, most experienced astronomers aren't gutsy enough to do that. And so they'll maybe do it for 5 seconds just to get the diamond ring, and then they'll put the filter right on. But I have determined that over numerous eclipses over decades, you can actually keep it on for longer, and you're not going to burn the you're not going to damage your sensor.
All right, thank you.
Okay, I see a question over here. Hang on a second, Michael, while I walk over with a microphone.
Sure.
Hey, how's it going? That was a great presentation. Thank you.
Very welcome.
I'm going to be taking a group of students ranging in age from 4 to 18 to see the eclipse at Six Nations. It's going to be wicked. But if you were making a speech about eye safety to that group of kids, what might you say?
What I would say is this, and this is actually a very interesting question, because in 1984, we went to Papua New Guinea to see a 53-second eclipse for a very specific reason. And there were kids there, and as you might imagine, there was not necessarily a lot of scientific understanding and no equipment and so on. And of course, they have been told, it's dangerous and all of that. And we had our kids, we had the kids out the day before, because we were camping there the day before, with eclipse glasses, that they put on, and we talked to them about it and said that it's perfectly safe if you put these on. There is, and what I have said is this: there is this completely unjustified feeling that during a solar eclipse, for some reason, the Earth is bathed in some kind of special lethal radiation that occurs only during a solar eclipse. Well, that's nonsense. It's no different than just watching the sun at any other time. And when we go out on a sunny day, we don't hear on the news every morning, it's going to be sunny today, use your solar filters, don't look up at the sun. Of course we don't hear that. Why? Because the sun is so bright that we're prompted to look away as soon as we look up. We see it, oh yeah, it's sunny, and then we look away. Way before there's any danger of any eye damage at all. The reason that people talk about it during an eclipse is that people go to extraordinary and often stupid lengths to try to filter the sun so that they can see it for an extended period of time. And if you don't use the right solar filter, then the infrared light will come right through. For example, using in the old days exposed and processed black and white film that just allows the infrared to come straight through, even though the brightness level seems to be perfectly fine, so you can look at it. And smoked glass and all of that kind of stuff from years gone past. So that's what I would say. Yes, you have to be careful, but don't think that this is super dangerous. It's just not. And so that's the way I would put it. I think that we, especially with younger people, we need to have them careful, but we don't want to panic them, and because it's not necessary. It really is not necessary. Now, I think you want to have a sort of one adult for at least 10 kids or something like that, because you got to make sure that people, and young kids don't necessarily know what they're doing. They're going to be kibitzing. They may have tears. They may be poking around and put a tear in their glasses. You got to be careful about stuff like that. So supervision is important, but fear mongering is not, and I think it does a disservice to scientific understanding. That's my view.
Thank you.
Any more questions for Michael? Well, while people think about it, I have a question myself, Michael.
Sure.
I've never seen a total solar eclipse, so I'm really looking forward to it. And I'm wondering, how dark does it get?
Oh, that's such a good question.
I'm thinking, is it like nautical twilight, civil twilight, astronomical twilight? What do you think?
All right. I'm going to answer that in a couple of ways, but the first is it really depends on the particular eclipse. And what I mean by that in particular is this. If you have an eclipse where totality is of short duration, the basic reason for that is that the moon is further away than an eclipse of long duration. For example, the great 1983 eclipse across Africa, which was a 7-minute eclipse, the moon was almost at perigee and much larger than the sun. And the consequence of that is that the width of the shadow, the upward shadow as it fell on Earth, was a lot wider than it's going to be at this eclipse. So at this eclipse, for example, in Texas, it's going to be about 180 kilometers wide. And that's fairly wide. And the point is that when you look down during the total phase of the eclipse, if you look around at the horizon, you will see sunset colors, sort of orangey colors all the way around, because you're looking at the part out of the sky outside of the shadow all around you. For a long eclipse, that's going to be a much wider shadow, and the light from the horizon is going to be much less. And so it really depends on the eclipse. I expect that this eclipse is going to be somewhat darker than the August 2017 eclipse because it's longer by about 2/3, and therefore the shadow is going to be wider. And what I would say is that it doesn't get as dark as you might think. I would say that the darkest is probably as dark as it gets during a fully moonlit night, a full moon. I just don't have any trouble, seeing stuff, doing my settings and all of that kind of stuff. Now, you look up and you see this. It's just unbelievable. This black hole in the sky, and the black hole of the moon actually seems to be darker than the surrounding sky. So that's what I would liken it to. You will have no trouble, finding something that you're looking for, picking up your binoculars or anything like that. But it does get dark. You won't notice it getting dark, and this is another really interesting phenomenon, until only very few minutes before the total phase starts. And why is that? Even though the moon has about an hour and a half, an hour 20 minutes, when it's gradually crossing the sun, and thereby obviously diminishing the light level, sort of arithmetically, to 50% and 25%, what happens? Your eyes open up, right? Iris in your eye opens up, and because it's trying to compensate for the lower light level. And only when your eye is fully open and the light continues to diminish will you then perceive that the light is actually diminishing. And so you don't actually notice it until about 10 minutes before totality, which is a really interesting phenomenon I've never actually heard described, but I figured it out myself from what I have observed. So I answered a little more than you asked.
Great information. Thank you, Michael. We have some more questions in the room.
Actually, this is a comment on how dark it gets because I saw the eclipse from Tennessee and we were in a park and there was a park shelter. So I thought, looking outside at the field in the open area, it looked like it wasn't getting that dark. But then I realized, and this was like maybe 15 or 20 minutes, looking under the shelter, my heavens, it's pitch black under there. Wait a minute, there's something funny going on.
I take it you got a clear sky?
Yes, we did.
Oh, well, good for you. I'm delighted to hear that because, of course, the weather prospects for Eastern North America were not as good as for the West. And yet from people I've heard who were, in those areas, Illinois, for example, as well, Carbondale, which is sort of Eclipse Central, it actually turned out to be good. So good for you. I'm delighted to hear that you saw it.
Thanks. Oh, next person.
Hey, Michael, great chat. Now we were talking about the light difference. Now, what about noticeable temperature difference?
Yeah, that happens as well. Although I'm going to tell you, I'm so wrapped up and so excited that I just want to pee, that I don't notice that. I just don't. And so, for example, at the October eclipse that I drove down to Texas for a quick trip down to see that, it was 13 degrees, but I was just in a t-shirt. And so, yes, you do notice that for sure. And you will notice if there are birds around, you will notice that they do go into the trees and they go to roost. And so you do notice that, but I don't think that it tends to be as significant an effect as people sometimes talk about.
Okay, thank you, Michael. Any more questions in the room? Yes, we have one more. I'm walking over with a mic. Hang on. Here we go.
How realistic is it to try imaging 12P comet during the totality?
Sorry, imaging what? I just missed
The
that.
12P Pons-Brooks comet.
That's really hard to say. And actually maybe should ask Arnold because he was talking about this. I don't know what the projected magnitude is going to be, and so I think that there's probably a decent chance with an appropriate focal length lens of getting getting the head of the comet, the coma. But how much tail you would get if there is, decent tail showing there, I just don't know. But I think that what you want to do for sure, is really bracket like crazy, so that you use long exposures, and you may completely burn in the solar corona, but that gives you your best chance. And so I would say it'll probably sort of, at 8 or even 10 exposures from one that will get the corona, and then that will expand it, and so on. Fortunately, you're going to have enough time to do that because, well, in most of the U.S., the eclipse is long. The total phase of the eclipse on the center line is longer than 4 minutes. Here in Toronto, it's about 3 minutes 40 seconds, I think, something like that. But of course, or in Niagara. So you are going to have time if that's what you want to try.
Thank you.
Okay.
We have one question here.
Hi, you mentioned you went to a bunch of eclipses, and around the community around it, with their setup, how do people approach you a lot, asking you about, a lot about the questions, or is like you find there's enough time to just talk with people about everything happening as throughout the event?
That's a really good question, and I guess what I will say is this: depending on where you are, obviously, an eclipse can be a great social event, and obviously I've done this a lot. I've seen a lot of eclipses. I've been a member of the society for over half a century, and it's a great pleasure to be able to go and talk to people. And you saw a photo of my setup. You hardly ever see setups like that at eclipses, and so you can imagine that everybody wants to take a look. What are you doing, and all of that. And it's a great opportunity to talk to people as well. I always try to take my main mount with my telescopes, and then another mount with a smaller telescope, just to let people look at it. And so they just line up, and they look through another telescope. And that's why I drive to these things. And so it can be, it can be a really good social event, and also an educational event. But what you got to be really careful of with your equipment is you have to tell people to stay back and organize them so that they stay, in a line. And if you're experienced enough, then you can do your photographs and then talk to them, and do your photographs and talk to them. And then I say, starting 5 minutes before totality, I'm not talking to anybody. I got to concentrate or I'm going to mess it up. And you just tell people that, and they do understand. People are just fascinated. If they're traveling a distance to come to see this thing, they're interested in it, and they will respect your equipment, the information you give to them, and the courtesy that you extend to them as well, which I think is really important as ambassadors of the largest national astronomical organization in the world, which is what we are.
Great. We have an online question.
Hi, thanks. Atul Dave says, when should we remove sun protection glass? I'm assuming that the filter.
Well, I think I've sort of tried to answer this at least twice before during this talk. Like I said, I take off the filters off my telescope. So the same thing applies then to a camera lens or visual or binoculars, for example, 20 to 30 seconds before totality, and then put the filters back on 20 to 30 seconds afterwards. Now, I'm able to do that because I have a lot of experience and I know what it's like during that period of time. If this is your first eclipse, then I wouldn't do that. I would take the filter off 10 seconds before totality. That way, at least, then you'll look up, for example, in binoculars or through a telescope, and you'll see the diamond ring and the corona. You'll see all of that, which you won't if you don't take your filter off a few seconds before totality. So don't worry at all about taking it off 10 seconds before. Do not worry at all about that, and keeping your filter off for at least 10 seconds afterwards. I do it longer, but that's just me.
There was also another question about good locations, and because everyone's going to have questions about that, where would be a good website to go for the map of good locations for viewing?
All right. The way I would put it is this. I I have, and the people who are going to be with me, have 3 general observing locations. On the and this may sound like it's not an answer to the question, but it's going to be. On the Friday before the eclipse, Friday the 5th, we're going to drive from Toronto to St. Louis, 1,200 kilometers. We're going to stay overnight there. Overnight, we are going to look at the at Astrospheric, a astronomer's cloud forecaster, and we are going to decide that we are going to stay there in the so-called quad state area and then observe from Missouri or Illinois, or we're going to retreat back up to Cleveland because the south shore of Lake Erie has for Canada and the US probably the second best chance, believe it or not, of actually a clear sky, or we're going to get up at 4 in the morning and leave and drive to Texas. We actually hope that we get to Texas. And I've got, I think, 6 specific observing sites set up, which I have figured 6 of them there, another half dozen in Illinois and Missouri, and then I think 5 or 6 on the surrounding Cleveland, using a combination of Google Maps and eclipse prediction software, which shows exactly where the center line is going to be. And what are you looking for? You're looking for parks, right? That's the first thing that you're looking for. And there are a lot of municipalities that have parks. You don't know, and we just don't know what it's going to be like. You're going to have to get there really, really early because the roads may be jammed. Michigan for the last year has been just terrified about what's going to happen. In Texas, they are expecting somewhere between 1 and 1.5 million people to come into the state for this. It will be by far the most widely observed eclipse. The interstates are going to be completely jammed. And what you want to do, if at all possible, is the night before the eclipse, you want to be situated inside the path of totality, in case the roads are just completely jammed by eclipse goers. Now, fortunately, by the time it gets here to Toronto, it's going to be about 3 o'clock in the afternoon. And so what you want to do, if you're heading down to Niagara, you better leave at 6 a.m. and get into the path, get to a park, get to a place where you can go to the bathroom during the day and set yourself up there, take a cooler and all of that kind of stuff. But you want to get there early because Niagara is going to be, to use an astronomical expression, nutso.
All right, why don't we stop there? And
All right.
We'll thank Michael once again. Great having you.
You're very welcome. And listen, I'll simply say for all of you who are going to be traveling to see the eclipse, good luck. And I hope we get clear skies for everybody. Okay?
Thank you. You too.
All right. Bye-bye.
Bye-bye. All right. So that wraps up the speakers for this evening. We'll take a short break and we'll switch over to the computer here for the announcements. All right. Well, thank you very much. And thank you very much to all of our speakers. So let's get the announcements going. So we've got 2 types of meetings here at the Toronto Centre. You've just been joining us for one of our recreational astronomy nights. And in 2 weeks' time, we're going to be having one of our speaker nights online.
Those of you who are joining us on YouTube, please say hello in the chat, enter some questions for presenters as others have done. If you are a new member of the Toronto Centre, please introduce yourself. And if you're coming to us from far outside the Toronto area, please let us know where you're coming from. So our next speakers night is going to be in 2 weeks on the 20th of March, 7:30 p.m. online only. Mariana Veltri of York University will be talking about galactic powerhouses, exploring quasars and their spectacular spectra. So live here on YouTube. Then coming up on the 3rd of April at 7:30 p.m., Andy Beaton will be talking about the sky this month. Ralph Chu will be introducing the EC Carr Astronomical Observatory for the coming summer season. And as Paul alluded to earlier, we have one open slot. So if you'd like to say something, like to present something, please drop Paul a note. Reminder of this presentation is in person at the Science Center and online. Coming up here at the Science Center this weekend, we've got solar observing on Saturday, 10 a.m. to 12 p.m. Last weekend's event was clouded out, so we're trying again. So just out front of the Science Center, we'll have some telescopes set up, filtered telescopes, as Mike was talking about, and you'll get a chance to take a look at the sun. Hopefully that's going to be doing something interesting that day. Also, it's a weather-dependent event, so please check our website for a go or no-go before heading out. Now, city observing sessions. The Long Branch Park pilot project is still underway. So if it's a Friday, Saturday, Sunday, or holiday evening with what looks like good skies, please take a look at our website and see if we have a event going on. There'll be a go, no-go mentioned on the website based on the weather. So things are busy at the DDO for March break. We've got Space Action Craters and Comets on Saturday, March 9th from noon to 2 p.m. All events require registration online. Costs and sign up. Cost is listed here, and you can register. The links are at rasto.ca. DDO Astronomy Sun Fun on Wednesday, March 13th, noon to 2 p.m. Again, registration online, links at rasto.ca. Out of This World, the Solar System, March 14th, 10 a.m. to noon. DDO Astronomy Family Night, Friday, March 15th, 8 to 10 p.m. Then we have on Saturday, March 16th, we have multiple planetarium events. We've got 2 sessions of Planetarium Day for little astronomers, 9:30 to 11, 11:15 to 12:45. And then there's the session for adults, 1 to 2:30 p.m. And then Astronomy Speakers Night on Saturday, March 23rd from 8 to 10 p.m. The DDO team will be talking about what causes a lunar eclipse, because as Mike and Arnold have both said this evening, we've got a penumbral lunar eclipse on the 25th. The CAO is open. The road is plowed, but as you heard earlier, there are some ruts in it. Yeah, there are some ruts in it. But operations are barging back to pre-pandemic conditions. We are still asking, though, that maximum of 2 unrelated persons per bedroom, mutually agreeing to share said room. And masking is still recommended and encouraged, but the preference of the people in attendance will be taken. Please take a look at the CAO bookings page for details before making your booking. As always, we're looking for some additional bodies. The RASC Toronto Centre is volunteer powered. So we're looking for a volunteer committee chair, marketing committee chair, and committee members. And EPO is always looking for additional help to help with star parties, presentations, and to operate telescope cameras. Reminder that in order to volunteer, you must be first a member. Drop me a line if you'd like to help out. This is the part where I get to plug RASC membership. You can sign up for the Royal Astronomical Society of Canada on the national site, or renew, secure.rask.ca, and gift memberships are also available. Contact the national office at mempub@rask.ca. Now, this would be the part where I normally invite you to join me for the meeting after the meeting. Unfortunately, the granite is currently in winter hours, which means the kitchen closes at 9:30 and the bar closes at 10. If you'll notice what time it is on your watch, it ain't going to happen. And also, they're not even taking reservations for extensions anymore. So the meeting after the meeting is going to be postponed, unfortunately, until after the May recreational astronomy night. I'm sorry to say. With that, I'd like to wish you all a very pleasant evening. Thank you very much for joining us, both live and on YouTube. Please follow us on all the forms of social media we have listed here. If you like what you saw on YouTube, please like and subscribe, click notification bell. And as always, be safe and keep looking up. Good night, everyone. Folks, just before we disappear, 2 pieces of in-house business.